as we start to work with three-dimensional space, it's important to be oriented about how the space is kind of put together. For one thing, notice that whenever you use your right-hand rule and turn your fingers along the x-axis and turn that into the y-axis, the thumb should point at the z-axis. Okay, so it's important always to remember that we have a right-hand rule coordinate system. So that this figure is just really kind of helping us identify what different planes in the figure look like. For example, the xy plane is a horizontal plane, the xz plane is a vertical plane along the x-axis, the yz plane along the y-axis, and let me put them all on here, and we end up with a figure that shows 8 different quadrants. So it's not really critical that we talk about what the numbers are as far as which quadrant is which one, but just remember that the first quadrant is always all variables are positive. X is positive, Y is positive, and Z is positive. And then we kind of work our way around, and let me just pick one at random here. The fifth quadrant, X is positive, Y is positive, but Z is negative, right? So we kind of are hopefully able to kind of start working with the ideas of a three-dimensional space. So that in the three-dimensional space, that we want to be able to define vectors, right? So this is a two-dimensional vector, and it's just really kind of talking about how we can define any two-dimensional vector by a combination of unit vectors. A unit vector in the direction I, which is in the x direction. So this vector I here would be written as bracket 1 comma 0 bracket as a vector, and the j vector would be written as bracket 1 0 comma 1 bracket, so that those two kind of elemental definitions allow us to define any vector in this. They're just limiting this to the first quadrant for right now, but that's the idea. So now if we go back to a three-dimensional space, that we can use that same idea about defining vectors. In this case, I'm moving only along the x-axis, and you can see that only the x component is changing. And similarly for the b-axis, I'm moving along, or I'm sorry, the b parameter here, and that moving along the y-axis, and then in the z-axis. Okay. So one thing that's important is that if I want to define a vector on the xy plane, all I need to do is just to set that z component to 0. And then let me kind of move it away from the, I guess that thing's always going to be in the way there, but that you can see that that z vector is a 0. So you can put a vector on a plane merely by taking off the component that is off the plane. In other words, I'm adding now z, so I'm going off the xy plane, and I'm back on the xy plane when z is 0, and then down below there, right? So kind of orienting yourself in three-dimensional space. Okay, so then the next figure is we're looking at, well, now let's talk about planes and move that value back and forth. Oh, I guess I'm only changing b here. So that as I go back and forth here, I can define a whole plane. You can see that the only component that's changing is the second component, the y component, right? And if I look at now, let's see, that I move an x-plane back and forth, right? So it's a little hard to see. Let me kind of just get it right on there. Is that one of the things that we'd want to be able to do is to define, give an equation for the line of an intersection here, right? So what's the equation of this line along here? And that would require getting a point on the line and a vector pointing in the direction of that line. And we'll talk about that a little bit more later as we get into lines in space. Okay? So that this three-dimensional kind of orienting yourself is a very, very important kind of aspect of what we're doing. So that if we move into what a sphere looks like in three-dimensional space, you should probably recognize this type of equation from the equation of a circle. X squared plus y squared equals r squared in two-dimensional space. And now all we're doing is adding in the third component, z. So that a sphere is defined as the shell, and the ball is defined as the shell plus the interior. So obviously we can change the radius. Let me get it a little bigger so we can see it. And then just move this ball around in space. So you can see how a vector gets defined. They're talking about, this figure is referring to a volume in space. And that if I show these grids, you can see where the sphere is located in space. Okay, so that we'll talk about how to incorporate these type of figures into our calculations. So that the parallelogram rule is to talk about how to add up two vectors in three-dimensional space. And in general, we do it component by component. So you can see that the blue vector is above the xy plane while the v vector is below it. So all I did is now we're going to add u plus 2v and double the vector v so that this black point, the green one, is the original. And then as we add these, all that is this dashed line moving along here is just this 2v translated to the head here. And we create the u plus 2v vector by 2, 6, minus 4 plus 0, 1 plus minus 2 gives me my resulting vector. So the vector arithmetic is straightforward, but it's just sometimes a problem kind of getting oriented in space. So one of the things that we want to be able to do, let me go back to the previous figure just for a moment here and take this off, is that we might want to know, well, how much of the component v, or vector v, the original v, lies along the u vector. In other words, a projection. And that's one of the values here that we use, that we take when we do a dot product. In other words, I can talk about the scalar component, u cosine theta, and the v component, the projection component, which is how not only the scalar part, norm of u cosine theta, but then also a unit vector in the direction of v over the length of v. So that this parenthetical expression is our unit vector, which takes kind of the place of our unit vectors I and j when we're talking about in our rectangular coordinates. So in this particular case, I can talk about any value or any amount of how much of the vector u lies along the direction or lies along the vector v by taking a scalar component using the cosine of the angle between them and the unit vector in the direction of v. Okay, so that the final thing I want to leave you with is now talking about the cross product. So an important thing to remember is that dot product is a scalar and the cross product is a vector. So in this particular case, I can manipulate the vector u, which is the red one, going up and down. So now here I'm just going to go back and cross it across the x-axis, move it off the x-axis in the xy plane, and then move it in the z plane. And that's kind of hard to see unless you kind of rotate a little bit. So you can see that the vector is going off of that plane. Okay, and I can do this, the vector u is going off that plane. And I can do the same thing with the vector v. Okay, so now if I look at the cross product, let me just reset this to where we started. And that, is that I want to look at these two vectors u and v and what their cross product does. So the cross product is another vector which is orthogonal to each of those two, right? So as I move this vector u, let me move it off the xy plane by increasing z. You can see that that green resulting cross product vector is changing because it remains a orthogonal to both the u and the v vectors. Okay, and even if I change v in some way, I can get a different vector. So now that since I changed v to go negative y, I get a vector pointing downwards. Okay. So one of the values of the absolute value of this cross product is it's the area between those two, described by the rectangle of the two vectors, the norm of u, or the length of u, and the length of v times the side of the angle between them, which is that cross product definition. So that the cross product is a vector, the dot product is a scalar, and it gives us a lot of tools to work with vectors in three-dimensional space. Okay.